Hello everyone, you're on the pick of the week and I've made specific selection for you guys. It's all about range estimations. So you can probably apply calculus and you can differentiate functions, find local maximum, local minimums, and in this case you can identify the maximum and minimum points, or basically let's say turning points for the function on a given x span or on a given domain. So I would rather explore the range estimations versus applying standard calculus approach. Let's have a look at the problem. For the following function, you need to estimate its range. So basically, from which minimum to which maximum point or y values it can be set up. Because you are not specified for x values, so we assume that x is simply can be any real numbers. So that's why we're saying that x from real numbers from negative infinity to positive infinity on the whole span. All right, and which way we can do that? And for example, applying calculus versus applying estimation, where estimation might work. Why I'm thinking about estimation? Because estimation might work much faster than applying calculus. Or probably in some problem, it's really hard to get the precise solution for x. When you get the equation for derivative, you equate to 0, and you're looking for a solution. Okay, so pause the video, try to do by your own, and let's get started. So for example, if we go in a classical way, what we actually need to do, let's take derivative first, f prime from x. But before we're doing that, I just slightly rearrange and I set up sine x plus cos x as one part of the function. So I'm taking derivative from that. Let it be q from s. And let's set up another function, which is sine 4x plus cos 4x squared. So, but instead of using that, I first square this up and I write sine squared 4x plus double product sine 4x cos 4x and plus cos squared 4x as well. So that's going to be, we're taking also derivative. This is r from y, I put s, so this should be of course q from x and r from x. So in that case, we need to differentiate two functions. With the first one, there is no problem. Second one is slightly complicated, so that's why I just want to say using the base trig identity that it will give you a 1, so that's why I would put sine squared 4x and cos squared 4x. That's going to be 1, and in this case, when we differentiate, we'll get 0 from 1, and we also get the sine of double product, so 4x, that means you've got 8x, okay? Sine of 8x, using again trig identities. So that means it would take f prime from x, from our function, we'll get cos x minus sine x. In that case, that's basically q prime from x. And we also differentiate the second part of the function r prime from x, which will give us the following, because this is 1, so we can rewrite r from x just shortly as 1 plus sine of 8x. So this is the second function. And now we differentiate, so that means we've got 0 from 1, and we've got 8 of cos 8x. That will give us r prime. Okay, so right now we have basically several trig functions, and we equate to 0 in order to solve for x. Now we need to solve for x. Solve for x. If you do have GDC, of course, you can solve and get solutions. then you plug back solutions, and that's how we can estimate the range. Why I'm thinking about finding local maximum, local minimums. So it's all about sine x plus cos x, or in other words qx, as the limited function. It has upper bound and lower bound, the same as for the second trig function. So that's why we can simply estimate, and we can say that for the whole span, for the whole x values from real numbers, in other words x from negative infinity to positive infinity, we do have periodic functions which is limited. It has upper bound and lower bound. So that's why we definitely have estimation for the range. So if you use GDC, you'll be able to solve, you'll be able to find x, those critical points. In other words, you can find turning points. Then you estimate it's going to be max or it's going to be mean. But in this case, I would just get rid of this approach. That's the classical one, and I'll try to apply estimation. Let's move to estimation. Having that, we have qx function, which is sine x plus cos x, and we have rx function, which is simply 1 plus sine 8x. Let's just rewrite. So this is r from x, and this is, so let's move back. So qx first, yeah. So that's going to be q from x, and that's going to be r from x. But r from x, this is the original one, but we rewrite as 1 plus sine 8x because that's shortened. Definitely shorthand will help us in terms of investigating the limits. All right, and let's start first exploring with qx, which is sine x plus cos x. So I dropped the graph, but obviously we can estimate in our standard case. So q from x is sine x and cos x. So we definitely know that the max value is definitely not 2, because for no one argument x, both sine and cosine will give you 1, right? So that's why we need to explore by taking derivative. And on the previous step we already did it, and that means we've got cos x minus sine x. So we equate to 0 because we're looking for extremum, so extreme points. That means we're looking for local maximal and minimal points. So right now we come to the equation sine x equals cos x. Then we can say we divide by cos x if it's not equal to 0. If it is so, so right now we've got tangent, we've got tan x equals 1. But when cos x is not equal to 0, but if cos x equals 0, we definitely can figure out that in that case sine x cannot be equal to 0, right? Sine x cannot be equal to 0 for the same x. So that's why definitely we're sure that cos x cannot be 0. From there we find out x as pi over 4 plus pi n. All right, so that's basically a set of critical points, and right now we can mark them on the graph. So here is the first one, here is the second one, and they have their round periods, right? So in that case, for sine x plus cos x, if we put x1 equals pi over 4 and we plug back, we'll get q from pi over 4 is equal to, so what I will put, each function sine x and cos x will produce square root of 2 over 2, and because we add them we'll get square root of 2 as the upper limit. So q from pi over 4 is going to be the upper limit, and we can drop the horizontal line at the level of square root of 2. So this is the max point. Of course, the same is going to be negative. It's going to be negative square root of 2, and it should go on this way. So this is negative square root of 2, and that's the minimum possible value for this function. So that means q from pi over 4, so when we plug n equals 1, we'll get pi plus pi over 4. We'll get to the next minimum, which is going to be negative square root of 2. Okay, it will plug, or you can check by plugging the values. So actually, the function has the period, so every time, the period is definitely 2 pi in that case. So every time your maximum point will be repeating. And we found the upper and lower bounds. So that's why we can say this is the upper bound and this is the lower bound. Okay, let's move to the next function. So the next function is sine 4x plus cos 4x, but on the previous step we set up that r from x is 1 plus sine 8x. So this function is more frequent, basically sine 8x lifted up by 1. So we definitely know that without taking any derivative, we can estimate that max value for the sine 8x is going to be 1. But together with 1, it will give you 2. So that means upper bound for the function, upper bound, is going to be 2, while lower bound is going to be 0 because the mean value for sine 8x is going to be negative 1. So it's more frequent function, so that's why we can estimate the periods. For the 8x, let's say it equals to 2 pi. So that's the expected value for x to have the period of 2 pi. But for x value, it's going to be pi over 4. So that means every pi over 4, it will have the period, right? So pi over 4, we estimated correctly. Yes, exactly. So from there to there, we have the period. So that's the period. And it looks like pi over 4, if you have a look at the picture. So, and it just values lifted up. All right. So we estimate upper and lower bound for each functions. And right now, what we're going to do, our resultant function fx is simply superposition of q from x and r from x. So that's why when we assume that the maximum possible value, if we don't care about whether they truly, like, we don't care about the true value because that's about estimation. Now we can estimate. So now we can estimate that upper bound, so upper bound for fx is going to be where you have max for q and max for r. This is, again, estimation. It's not really truly true value, but it might be very close to it. So right now, I'll just give my estimation, and then we will have a look at how real graph goes through using GDC. And later on, I will give you an idea how you can also explore to maybe give a more accurate estimation. So Q max and R max. Let's go back. So we've got, for Rx, we have upper bound 2, and for Q max, we have square root of 2. So that means it's going to be 2 square root of 2 plus 2. This is the upper bound for fx. What about lower bound? So lower bound, it's going to be Q mean plus R mean. In that case, for Rx, we have 0, that's the lower bound, and negative square root of 2. So that's why we can estimate as negative square root of 2. Hence, as a result of a superposition of two functions, we actually have square root of 2 plus 2 as the upper bound and negative square root of 2. Okay, So what we're gonna do now, here is the superposition depicted on that picture, and we'll see that if we lay over both functions and if we lay over both functions and trying to depict how they go, we see definitely that this is the maximum for qx, and this is the maximum for rx. We're definitely sure that for the maximum of our function qx, there is no maximum value. So in other words, you can check in this way. For example, you estimate you have the maximum value for your function, for your qx. So this value is square root of 2. But there is no other maximum values for your rx. So that's why the upper bound, which is square root of 2 plus 2, cannot be reachable, right? It can be reached by the actual function fx. So this value is the value that your function fx cannot take. So that means fx is always less, let's set up f is always less than square root of 2 plus 2. But of course, you also need to check when your function rx has the maximum value. So in this case, this is 2. So you need to add with the value what if you plug into your function, let's mark as green, so this x value. It's around 1, so this is x around 1, but of course you need to estimate using your solutions for q, for let's say, where is that? For rx, 1 plus sine x. In this case, you have set of values. So in this case, x equals pi over 4. That's the nearest one, and it has so this is the period, right? And you also need to estimate the nearest maximum. So in that case, it's definitely when sine takes the maximum value. So in this case, 1. It takes when the nearest one, x1, is equal to, so 8x so 8 times x1 should give you pi over 2. In that case, pi over 16. So I bet that this is the nearest value for the maximum, okay? So x equals pi over 16. So that means, going back to combined graph, so that's the nearest, plus pi over 4, that's going to be the next one. So that means this value is pi over 16 plus pi over 4, which will give you the maximum value for rx, all right? And then you need to plug this value into your q function in order to get the idea what's the true value for that. And if you add them up, you need to check for the absolute, like your estimation for the absolute max value, max possible value the function might take. So, and you also check that it's going to be less. Just take calculator and try to check it. So the same story is about minimum. So I just show you combined graph. So that's the max value, which is 2 plus square root of 2. So that's combined graph for your function fx. And if you have a more precise look what's going on at that point and at that point, you'll see that the maximum value is not reachable, okay? So this is their local maximum for at least for the period. So we are estimating that value, and you see this point is lower than the value of 2 plus square root of 2. So where estimation might take the place, it might take the place when you have multiple choice questions, and for this, like for example for an Oxford test, for JEE Mains, even for A-level and IB programs, so where you might have like more complicated, like gold questions, the hardest one, okay? So that means it's going to be powerful tool for estimation, so you can briefly estimate the boundaries, lower and upper, and probably choose the answer which is most appropriate in your case. Okay, so that's the same story as I said about a minimum. So the minimum value, as we established, as negative square root of 2, and this value is also not reachable. So again, you need to check combinations. So just going back, you need to check combinations for the local minimum for your Rx function as well as with Qx. So that will give you an idea that negative square root of 2 is not reachable value for the function fx. So this is a resultant graph. If you do have GDC, if you are able to use GDC, of course you need to use that. But in terms of estimation, you need to give your work out how you actually worked the solution, how you worked estimation, and what's the real basis for that. I hope I helped you in some way. If you do have like similar problems, or at least I'll give you an estimation tool how and which way you can explore more tricky, more complicated functions. That was specific selection for you guys. If you're new here, subscribe please, and like this video and share with other people who are struggling with similar sort of questions. That was Daniel Dallas, and see you next time.